Okay, well, you did show up late and you're drinking something you're not supposed to in class. Okay, I'll just count you tardy for the late showing up. I'll just put your drink up here. You're not supposed to have that either. All right. Sorry, video, I missed the intro. But we'll go through this. All right, number 1. 1/2. What kind of a number is 1/2? Not what it's equal to. Is it a natural? Is it an integer? Is it a whole number? No. It is a rational. Do you guys remember the letter that stands for rational?
Q.
Q. And on number 1, the directions said list all that apply. So if it is a natural number, do you guys remember me saying this? Natural numbers are whole numbers and whole numbers are integers. Integers are rational. So if it's a natural number, it's actually all 4 of those. It goes in all 4 sets. If it's an integer, or a rational rather, it's not necessarily any of those. 1/2 is not natural, it's not whole, it's not anything. So just rational, Q. Okay, number 3. 2, no, forgot what I was doing. Number 1A, B. All right, B is 7/1. Is 7/1 is just equal to what?
7.
So is that natural?
Yeah.
Yep.
So you're
Is it a whole?
Yes.
Yeah, we're putting all that applied. I said that. Is it an integer?
Yes.
Is it rational?
Yes.
Is it irrational? No, if it's irrational, it can't be irrational. And vice
So we
versa.
don't have to put real?
No, all of these are real. So no, don't put that. C is 0. Is 0 a natural number?
No.
No. Is it whole?
Yes.
Yep. Is it an integer?
Yes.
Is it rational?
Yes.
Okay. Yeah. So it's like the options are like one answer to up to 4. This is like the most. Because there's like 5 subsets. These 4 and irrational. Okay, D, negative square root of 195.
It's Q with the content.
Yeah, if you plug that in the calculator, actually square root of 196 is 14. So that one would have been like an integer. But square root of 195 is a mess. So that would mean it's an irrational. So rational Q with the not symbol. Not Q, not rational. Okay, negative 5 is a what? Integer. And if it's an integer, is it rational?
Yes.
Yes. But negative 5 is not natural. Okay, on 2, the directions are slightly different. They only want you to list the most specific set. So let's go back up here real quick. So natural is a more specific set than whole numbers because it has, well, one fewer option. Whole numbers are more specific than integers because, you know, there's more options. So you kind of want to go as high on the list as you can. But yeah, you only put one answer. So like negative 5, we would just put integer, even though it is rational, but more specifically, it's an integer. So one answer on number 2 for each of those. All right. Number 3. All right. Do you guys recognize this property? 3 parentheses 2 plus 7 equals 3 times 2 plus 3 times 7. Distribute. Oh, you stole it. Oh, man. Yeah, that's what the distributive property looks like. If you, yeah, all of these answers, by the way, are back on the previous page or 2. Luke, Steve. Okay, number 5, if x equals, this one that took the other class a little while to get. If x equals 6 and 6 equals y, x equals y. Lauren, do you have it yet?
Sorry, what?
All right, Luke, what is it?
Transitive.
Transitive property. Luke is the king of the transitive property. All other properties bow before him. Okay, number 7. Hey, give somebody else a chance, man. Okay, well, 7, even I would hesitate because I'd be like, was that commutative or associative? So 7 is towards the bottom of the orange box on page 78. Okay, it's not just the associative property though, it's the, you gotta be more specific because there's addition and subtraction. So you gotta say associative property of addition. Okay, like I said, I'm not gonna have you guys memorize this part. This is more like a warm-up for geometry proofs. Well, we're warming up for an algebra proofs, which are warming up for geometry proofs. That's what we're doing. Okay, number 9. If 3a equals 9, then a equals 3. Okay, yeah, so basically what they did is they solved this equation. How did they solve this equation though?
They divided 3 by a, and then they divided.
Okay, if you divide both sides by 3, what did I say that was called? Okay, even though it's division, they call it the multiplication property of equality. How'd you know all those, Luke? Somebody write the answers in there.
She's reading the back of the book.
Are you looking it up in the back?
No.
Oh, yeah.
You just paid really good attention.
Frozen.
What?
He's just following along. Yeah. You guys get that though? Are we good on that part? Okay, 10 through 15, always, sometimes, or never. These usually trip people up because you got to think very carefully about them. Because some, you know, anyways, number 11, an integer is a natural number. Is it possible for an integer to be natural? Yeah, because like the 1, 2, 3 part of integers, those are natural, and the negative part are not natural. So that is, you guys are right, that is sometimes. Okay. 13, an irrational number is an integer. Are there any irrationals that are integers? No. Irrationals are all, integers are rational, so they can't be irrational. Irrational numbers are never integers. They're always like infinite decimals that don't repeat. So that's never going to happen. There is no overlap between rational and irrational. Okay, number 15. A whole number is rational. Always. Luke's just good at these, man. Did you look up the odds already?
What?
Did you look these up?
No.
You just know them all? Luke always knows all the math problems. All right. Everybody's looking at you suspiciously.
Preston Curtis.
Yeah.
What? What did he say? What did he say?
Oh, we're not doing this next set. All right. The next section is 21. Okay, on 21. Okay, so basically we're rewriting the transitive property, but we're going to use greater than. That's what we're doing. So the transitive property originally said A equals B and B equals C, then A equals C. Okay, that's not what we're gonna put though. We're supposed to rewrite it with the greater than, because it does work for greater than two if you think about it. So if A is greater than B and B is greater than C, then what?
A is greater than C.
A is greater than C.
He is be cool.
Alright, let me see that paper.
Did
you do it all the time?
Jordan's kind of most suspicious.
What number is that, 21?
I didn't get to the rest.
You wrote all the odds down already?
Yeah.
No one. Where'd you get all the odds?
Yeah,
They're in the back of the book.
you didn't know that?
No, I didn't. I was just asking.
What?
Bro,
Okay, anyway, this is the actual answer.
we talked to you.
So if A is bigger than B, B is bigger than C, A has to be bigger than C. It works for greater than two. Okay, it's called the transitive property of inequality. 23, symmetric property of parallel lines. So let's flip back and look at the symmetric property. It says if A equals B, then B equals C. But we're supposed to apply that to parallel lines. So we'll say if line A, if line A, have I shown you guys this yet? This is the parallel symbol. We're doing a lot of parallel lines next chapter. We haven't really gotten into much geometry yet, but parallel lines, if line A is parallel to line B, then what? Okay, if we're following this pattern, I didn't even write it correctly.
Then line A is parallel to
Yeah,
line
okay,
C.
here's the original symmetrical property, symmetric property. If A equals B, then B equals A. So if line A is parallel to line B, line B is parallel to line A. Does that make sense? It works the same both ways, that's just what they're saying. Alright, on 22 it says perpendicular. Have I shown you guys the perpendicular symbol yet? Or have we even talked about what perpendicular means? I don't know.
No.
So,
Yeah, some of these things are kind of further down the road. So the perpendicular symbol is an upside down T. Perpendicular means the lines create a right angle when they meet. So it's kind of like 23, but just use the perpendicular instead of the parallel thing. Alright, then we're on to the proof. 33. Okay, it says complete the proof. So, this is what a formal proof looks like. So if you look at them, they kind of like did half of it for us, but this is kind of the outline that it uses. So on the left side, there's a column for statements, like there's stuff that you say. And then on the right column, it says a reason. So to do a proof, you make a statement and you say the reason that justifies your statement, like every line. You do a statement and say why you can say it. Do another statement, why can we say that? Do another statement. And they're kind of all connected and you kind of argue your way until you get to the end of what you're trying to prove. Okay, on 33, because this is kind of like an intro, they're like doing half of it for us. But we actually don't need, I'll show you, we don't really need their help that much. Get out of there. So the top of the problem before the statement says if 90 equals 3x plus 13, then what was it, x equals 17, 20, 30, yeah, that's right, okay. So this first part is what you would call the given. Like you always have to start by saying, this is what we know. And this last part is what we're trying to prove. This is what we're trying to get to. So, if you look at line 1 over here under the reasons, they say given. And this is pretty much how a proof always starts. You have to start with something that's been given to you, and then you argue from there. You make your case from there. So the given part on this one is basically the if part. We're assuming this is true, and then we're gonna argue our way until we get to that. So basically, we're doing an algebra problem right now, but you guys are familiar with these problems, so you're gonna kind of see what it looks like in proof form. All right. Now, if we were solving this problem last year, what would we have done first?
Property.
Right, distributed property. Need somebody besides Luke to go today. So it's,
I didn't even get that far, honestly.
so now you're doing it by yourself instead of with the books, is what you're saying?
Hmm?
Now you're doing it by yourself?
No, I'm saying we did that, I didn't even get that far yet.
Yeah. Okay, yeah, so he said distributed property, that would be the reason. Over here kind of goes the rules that we're using, the properties, the postulates, the rules, distributed property. That says it's okay to do what we just did. Okay, and then if we're solving, what would our next step be after that? If we're solving this for x,
Subtract 39.
you'd subtract 39. Now, I have seen it written like this. We're not going to do this though. Like where you show 39 equals 39, that you're subtracting the same value. And then over here they put the reflexive property because these two are equal, but we're not going to do that. We're just going to subtract 39, which is what I prefer. So 90 turns into 51. Okay, what's that called when you subtract the same value on both sides?
Addition property equal.
Yeah. Maybe Luke got a word in here. Addition property of. Oh, maybe that's why you're overheating, because your brain is just going 90 miles an hour.
Who, me?
Yeah. Your brain's on fire. Burning too much calories. Okay. Do you guys know your brain actually does burn calories?
It does?
Yeah. Not enough to lose weight, but, you know, it does. I think if you're like a champion chess player, you might actually have to eat a little bit more than, you know, somebody else. But for the rest of us, probably don't need that many. Okay, what's our last step here to solve for x? Divide by 3, which would make that a 17. And what's it called when you divide both sides?
Division.
No, they don't have a division. They call it multiplication property. Because dividing by 3 is like multiplying by 1/3, so they just call it all multiply. Okay, now, if I was doing the proof, I would probably stop right there, because this is kind of what we're supposed to prove, but it's a little bit different. What's different?
It's x equals 17.
Yeah, it's not 17 equals x, it's x equals 17. So they did flip it if you look in the book. And what's that called? If 17 equals x, then x equals 17? No, it's not reflective. No,
I'm close.
it's on the top of page 79.
Shoot.
If 17 equals x, x equals 17, that is, huh?
I'm actually stupid. It's right there. in the paper.
Oh, the book wrote it in? Okay.
I was
Yeah,
trying to get the answer by myself, wasn't looking at
it's
it.
the symmetric property. It doesn't matter which thing comes first when they're equal. Symmetric property. Equality, yeah, I suppose, but that's. Alright, does that kind of make sense? We're used to solving equations. We're not used to having to state what rule we're using every time. but that's kind of how proof works. Let me look at 34 real quick. You guys remember, I don't know if you guys remember how to solve an absolute value problem. Maybe I should do a real quick example. Well, let me start with this actually. If the absolute value of x is 5, you guys know what x could be right here? What does absolute value do to a problem?
Like if it's negative,
Yeah, what if it's positive?
and then there's just.
It stays the same, yeah. So it turns everything positive. If it was positive, it just stays positive. So if absolute value of x equals 5, what does x equal?
5 and negative 5.
Right, positive or negative 5.
Which isn't that like also like one of the ways to get imaginative numbers if you put like equals negative 5?
Huh?
If you put like negative 5 for the equals, would that be an imaginative number?
Not exactly, it just doesn't have a solution. Imaginary, that's like second semester algebra 2. It's not that bad, but yeah, this would just be no solution. You can't have an absolute value equal. You're not too far off, actually, kind of related, but no, that would just be no solution. Okay. So the problem that you're doing looks more like this. So we did some of these last year. You want to get the absolute value by itself first. So how would we, what would we do to get this absolute value by itself? It's almost the same as this. Almost the same as this. So what would we do here? Not a trick question. What would we do here? Plus 7. So same thing here. You want to get the absolute value by itself first. I'm not going to go through all the absolute value rules, but then what would we do after that? Divide by 2. Okay, and then what would we do after that? It would just be x is positive or negative 6. I think that reason, did they just give you that reason? Yeah, by the definition of absolute value. This last part is true, but the book gives that to you. I'm talking about 34. The reason for this last part.